curve is such that dy dx equals 2x squared minus 5. Given that the point 3,8 lies on the curve, find the equation of the curve. Okay, well, the first thing we should do is always identify exactly what we've been given so that we can know exactly what we need to do. Now, they've given us an expression for dy dx, which equals 2x squared minus 5. Now, dy dx represents a gradient function of a curve. We are required to find the equation of a curve. So had we been given the curve, we would differentiate that to get the derivative function or the gradient function, which is 2x squared minus 5 dy dx. To start at the derivative function and find the equation of the curve, we are going to be performing the reverse of differentiation, which is integration. So given that dy dx equals 2x squared minus 5, we'll be integrating this expression with respect to x. So integrating dy dx will just give us the function y. Integrating 2x squared will give us 2x to the 3 divided by 3. Integrating minus 5 will give us minus 5x, and we also need to include the integration constant, so we're going to add c. If you are not sure or need to refresh your integration techniques, there is a separate video in the description box below, so refer to that if you need to. So this is the expression now for the curve. We need to determine what the value of c is, and we do that by substituting the point that lies on the curve. Since this represents the equation of the curve, and we were given a point that lies on the curve, we would substitute this point into this expression to find the value of c. So substituting 8 for y and 3 for x, we have 8 equals 2 times 3 cubed over 3 minus 5 times 3 plus c. So 8 equals 3 cubed is 27, divided by 3 is 9, 9 times 2 is 18, minus 5 times 3 plus c. So c equals 5. The curve is therefore given by y equals 2x cubed over 3 minus 5x plus 5. Okay, find the gradient of the curve y equals 12 divided by x squared minus 4x at the point where x equals 3. Okay, we are given a curve, the equation of a curve, and we are required to determine the gradient of that curve. So we need to find an expression for dy dx, because dy dx represents the gradient of a tangent to a curve. Before we can differentiate this expression, though, we need to ensure it's in differentiable ready form. So by that I mean, if you have a denominator, your expression needs to be such that you have a denominator of 1. So y equals 12 over x squared minus 4x. So we're going to take this expression to the top. So we have y equals 12 times x squared minus 4x to the negative 1. This is now in differentiable ready form. So differentiating this function dy dx gives us minus 1 times 12 minus 12 times x squared minus 4x, and then we subtract 1 from the exponent, so it's to the power of minus 2. But using the chain rule, we also need to find the derivative of the contents of the bracket. So the derivative of x squared is 2x, and the derivative of minus 4x is minus 4. So we can clean that up a little bit. It's minus 12 times 2x minus 4 divided by, we're going to write this expression here as a positive power. It'll just be easier to work with. So this is now your derivative or gradient function. This expression represents the gradient of a tangent to the curve. Now at the point where x equals 3, we can determine the value of the gradient. So the gradient of the tangent to the curve where x, at the point where x equals 3, so minus 12 times 2 times 3 minus 4 divided by 3 squared minus 4 times 3, and that is all squared. So we'll have minus 12 times 6 minus 4 is 2, so it's minus 24. We'll have 9 minus 12 is minus 3 squared is 9. So your gradient for x equals 3 will be minus 24 over 9, which you can simplify as dividing through by 3, minus 8 over 3. Okay, question 3. Show that the equation sine theta plus cos theta equals 2 times sine theta minus cos theta can be expressed as tan theta equals 3. Okay, we have a trigonometric equation here that involves two trig ratios, sine theta and cos theta, and we need to reduce or simplify this such that we have a single trigonometric ratio, tan theta. So we don't have many options here other than to multiply 2 into the bracket on the right hand side. So that's going to be our starting point. Sine theta plus cos theta equals 2 sine theta minus 2 cos theta. Now bear in mind that tan theta is a quotient identity which equals sine theta divided by cos theta. So we want to get to a situation from this equation, from this expression, where we can have the ratio sine theta over cos theta. So the next thing we're going to do is get all the sine theta terms to the one side and the cos theta terms to the other side. So taking minus 2 cos theta to the left gives us 3 cos theta, and sine theta over to the right will give us 2 sine theta minus sine theta equals sine theta. And then we just simply divide both sides by cos theta. So 3 equals sine theta divided by cos theta, which is tan theta. Hence solve the equation sine theta plus cos theta equals 2 times sine theta minus cos theta for theta between 0 and 360 degrees. Now we've just shown that this expression here is equivalent to tan theta equals 3. That was the whole purpose of the previous question, was to establish a single trigonometric ratio from which you can solve for theta. So our reference angle theta equals shift tan 3. So theta equals 71 rounded up to a single decimal place, 71.6 degrees. Now because this ratio, tan theta, equals positive 3, it's a positive ratio, that means that our solution lies in either quadrant 1 or quadrant 3, where the ratio tan theta is positive. So our first solution will be in the first quadrant, so theta equals 71.6 degrees, or theta will lie in the third quadrant, where tan is also positive, which is the quadrant 180 plus theta, so theta will be 180 plus 71.6 degrees, which is 251.6 degrees. So that is the solution. Theta is either 71.6 degrees or 251.6 degrees. Okay, question 4. Find the first three terms in the expansion of 2 minus x to the power of 6 in ascending powers of x. Now, we only require the first three terms. So we could, in theory, expand this binomial completely, but we don't really need to do that because they're only asking for the first three terms. So 2 minus x to the power of 6 equals 6 choose 0 times 2 to the power of 6 plus 6 choose 1, 2 to the power of 5 times minus x, we'll just put to the power of 1 there, we don't need to, plus 6 choose 2, 2 to the power of 4 times minus x squared, and we can continue with 6 choose 3, 6 choose 4, etc. But we only need the first three terms, so it doesn't make much sense to expand this entire binomial. If you prefer, you can always use Pascal's triangle to determine the coefficients of each of these terms. And just recall that Pascal's triangle looks like this, and if you prefer using Pascal's triangle, then by all means use it. So these are the coefficients here, this last row, the sixth row. 6 choose 0 equals 6 factorial over 0 factorial times 6 minus 0 factorial times 2 to the 6, which is 64, plus 6 choose 1 is 6 factorial divided by 1 factorial times 6 minus 1 factorial times 2 to the 5 is 32, and we have a negative x as well. And then 6 choose 2 is 6 factorial over 2 factorial times 6 minus 2 factorial times 2 to the 4 is 16, and minus x squared is x squared. So if we just look at Pascal's triangle here, you can obviously go and work with factorials. We're just going to end up getting these coefficients over here. So the first 6 factorial divided by 6 factorial is 1, and we have 64 as our first term. Our second coefficient will be 6. So we'll have 6 times 32, which is 192 times minus x. So the second term is minus 192x. The third coefficient is 6 factorial divided by 2 factorial times 4 factorial is going to be 15. 15 times 16 would be 240 times x squared. So it would be plus 240 x squared. And just to reiterate, we don't have to go and expand the entire binomial because we only require the first three terms, which are 64 minus 192x plus 240x squared. Find the value of k for which there is no term in x squared in the expansion of 1 plus kx times 2 minus x to the power of 6. Now, the reason for the previous question for finding the first three terms of this expression here is that we only need the first three terms to answer part 2 of the problem. We're looking for terms in x squared. Don't worry about the semantics of the problem. We're looking for, at least for now, don't worry about it. We're looking for x squared, the coefficient of the x squared terms. So that is why we only required the first three terms of the expression, which was 64 minus 192x plus 240x squared. These are the first three terms. So when we multiply 1 plus kx times the first three terms of this binomial expression, we are only in this question, we're only interested in the x squared term, right? So when we multiply out these terms here, anything larger than x squared we don't need. So it was trivial and nonsensical to expand this binomial completely because we are only interested in the coefficients of the x squared terms. So when we multiply the first bracket by the second bracket, we can have 1 times 64. That doesn't give us a term in x squared. Multiplying the next two terms still doesn't give us a term in x squared, but multiplying 1 and 240x squared will give us 240x squared. So what we're looking for here is the coefficient of x squared in this expansion of these polynomials. Then multiplying the last term, kx, with the first term, 64, gives us a term in x. We're not interested in that. multiplying kx by minus 192x will give us a term in x squared. So we are interested in that. So it'll give us minus 192 kx squared. We're just looking at the coefficient of x squared terms here. And the last term, with the last term, will give us a term in x cubed. X times x squared gives us x cubed. We're not interested in any other term other than an x squared term. So this is our expression, which in x squared, which is what we're interested in. Now we need to find the value of k for which there is no term in x squared. So if there's not going to be a term in x squared, this entire expression would have to be 0 for there to be no term in x squared. So that's precisely what we do now, is equate this to 0. And we can just solve for k now. So 240 x squared equals 192 kx squared. We can cancel the x squared terms, and k equals 240 divided by 192 in simplest form is 5 over 4. So if k equals 5 over 4, then expanding this expression over here would yield no term in x squared. The diagram shows a rhombus ABCD. The points B and D have coordinates 210 and 62 respectively, and A lies on the x-axis. The midpoint of BD is M. Find by calculation the coordinates of each of the points M, A, and C. Okay, so we're given a rhombus ABCD. We're required to find the coordinates of point M, A, and C. So let's start with point M. M is the midpoint of diagonal BD. So that's pretty straightforward. So to determine the midpoint of BD, we use the midpoint formula, x2 plus x1 over 2, y2 plus y1 over 2. So that'll give us 2 plus 6 divided by 2. That's the x coordinates of M. And the y coordinate of M will be 10 plus 2 over 2. So that gives us the point 4, 6. And this is the point M. To determine the coordinates of the point A lies on the x-axis. A is a point common to line segment AB and AD. We could in theory use the distance formula. That could be quite messy and time consuming. A better way is to construct the diagonal AC. Now ABCD is a rhombus, and the diagonals of a rhombus bisect each other at 90 degrees. So we know that BM is perpendicular to AC. So we could use the gradient, determine the gradient of AC, the gradient of BD, and work that way. But I think even a better way to find the coordinates of A would be to use actually we can't use the midpoint because we don't know what C is. I was going to suggest using the midpoint. We can't do that. So we're going to have to determine, we've got a point on line segment AC, which is M, which has coordinates 4, 6. If we determine the equation of line segment AC, that line segment cuts the x-axis at point A, which is easy enough to find the coordinates for because x-intercepts have a y value of 0. So we're going to determine the equation of AC. We know that a point M lies on that line AC. So all we need to do is find the gradient of AC. Once we've got the gradient of AC, we can then determine the equation of AC and hence find the coordinates of point A. So to find the gradient of AC, we can use the fact that BD and AC are perpendicular to each other. That's a property of a rhombus, that the diagonals cut each other, they rather bisect each other at 90 degrees. So the gradient of AC times the gradient of BD equals -1. We know this because the diagonals are perpendicular to each other. So if we find the gradient of BD, we'll get the gradient of AC from this formula over here. So the gradient of BD will be 2 minus 10 divided by 6 minus 2, which is minus 8 over 4, which is -2. So therefore, the gradient of AC must be a half, because minus 2 times a half will give us -1. So we now have the gradient of AC, which is a half. We have point M that lies on line segment AC, so we can determine the equation now using y minus y1 equals m times x minus x1. If you prefer, you can also use the equation y equals mx plus c. This just requires an additional substitution, and you're going to get the same equation regardless of which equation you use. So we'll have y minus 6 equals a half times x minus 4, y equals a half x. A half times minus 4 is minus 2, plus 6 will be 4. So this is the equation of AC. Now we need to find the coordinates of A, and A is an x-intercept of that line segment AC. So for x-intercept, y equals 0. So 0 equals a half x plus 4. A half x equals minus 4. X equals minus 8. So A is the point, minus 8, 0. And to find the coordinates of point C, now we can go back to the midpoint. Since the diagonals bisect each other at 90 degrees, M is the midpoint of BD, M is also the midpoint of AC. So C is the point XY, A is the point minus 8, 0. Therefore, the midpoint of AC will be x2 plus x1 over 2. So it'll be x minus 8 over 2 and y plus 0 over 2. So x minus 8 over 2, y over 2 is the midpoint of AC, which is the point M. And we know that M is the point 4, 6. So therefore x minus 8 divided by 2 must equal 4, and y divided by 2 must equal 6. So x minus 8 equals 8, x equals 16, and y divided by 2 equals 6, y equals 12. C is therefore the point 16, 12. A geometric progression has 6 terms. The first term is 192, and the common ratio is 1.5. An arithmetic progression has 21 terms, and the common difference is 1.5. Given that the sum of all the terms in the geometric progression is equal to the sum of all the terms in the arithmetic progression, find the first term and the last term of the arithmetic progression. Okay, let's start with the GS, the geometric progression or geometric sequence. It has 6 terms, so we know that n equals 6 for the geometric sequence. The first term is 192, and the common ratio is 1.5, which is 3 over 2. The arithmetic sequence or progression has got 21 terms, so n equals 21, and the common difference equals 1.5 or 3 over 2. We're told that the sum of all the terms in the geometric progression is equal to the sum of all the terms in the arithmetic progression. So we're going to be summing to 6 because we have 6 terms in the geometric sequence or progression, and the arithmetic we're going to be summing to 21. So they're saying that the sum to 6 terms of the GS equals the sum to 21 terms of the AS. So there's one equation that we're going to use. Let's find an expression for each of these sums now. For the geometric sequence, there are 2 sum to n formulae. the sum to n equals a times r to the n minus 1 over r minus 1 when r is greater than 1, and it equals a times 1 minus r to the n over 1 minus r when r is less than 1. Now, because r for the geometric progression is 1.5, that's obviously greater than 1, so we're going to be using this sum to n formula. So the sum to 6 terms for the geometric sequence will be a 192 times r to the n, so it's going to be 3 over 2 to the power of 6 minus 1 divided by r minus 1, 3 over 2 minus 1, and that equals 3,990. The sum to n terms for an arithmetic sequence is given by n over 2 times 2a plus d times n minus 1. So the sum to 21 terms will be 21 divided by 2, 2a. I didn't write down the common difference here. Sorry, I did. I just wrote it as a. Wrote that incorrectly. D is 3 over 2. So 3 over 2 times 21 minus 1. So that equals 21 over 2 times 2a plus 20 times 1.5 will be 30. So that equals 21a plus 315, and that's the sum to 21 terms. So 21a plus 315, and these two expressions are now equal. So 21a plus 315 equals 3990, equals 3675, which means that a equals 175. Okay, we want the last term of the arithmetic progression, so we're looking for term 21, which equals a plus 20d. We know that because there are 21 terms in the arithmetic progression, a equals 175 plus 20 times d is 1.5, 3 over 2, 175 plus 30, so the last term or the 21st term equals 205. If there's anything you're unsure of in this video, there are detailed videos covering each concept in this video down in the description box below, so make sure that you check that out. Also, if you like this video, then please give it a thumbs up and subscribe to the channel. It really just helps the algorithm get my videos out there to reach a wide audience. Function f is defined by f of x equals 3 minus 2 sine x for x between 0 and 360 degrees. Find the range of f. Now, while it's not necessary to draw a sketch graph, it is a nice idea. It's very, very straightforward. When it comes to trigonometric functions, it's very straightforward to read the range of a trigonometric graph. So we'll start off by sketching the function y equals sine x. The reason we're starting off with y equals sine x is we are going to see how this function y equals sine x transforms into f of x. So if we just look at the function, the largest value of y is 1, and that happens when x equals 90. And the smallest y value is at negative 1, and that happens when x equals 270. So the function sine x has a maximum value of 1 and a minimum value of negative 1. That's by definition. Another way of saying this is y is less than or equal to 1, greater than or equal to negative 1. And yet another way of writing the range is in interval notation. So y is an element of square brackets minus 1 to 1. This is generally how range is expressed in interval notation. So that's the function y equals sine x. The next thing we're going to do is sketch y equals minus 2 sine x. So the blue function is the function y equals minus 2 sine x. The minus simply indicates that the function shapes like that as opposed to shaping like that. This is where your a is positive. So for your general function for sine, a is your amplitude. So if a is positive, then the function will shape from left to right, and if a is negative, it will shape from right to left. So the amplitude a is minus 2. That just means that the height of the function is 2 units. Minus, again, just means that the function will shape from right to left. So the range for y equals minus 2 sine x, we can see that the minimum value for the function is minus 2, and the maximum value for the function is positive 2. So y is an element of minus 2 to 2. Now for the function f of x equals 3 minus 2 sine x, f of x is minus a function minus 2 sine x transformed 3 units or shifted 3 units up. So the green function is now f of x, which is 3 minus 2 sine x. And as mentioned earlier, f of x is the function y equals minus 2 sine x shifted 3 units up. So if we take each point on y equals minus 2 sine x and we shift it up 3 units from minus 2 to 1, we will get the function f of x. So when x is 270, we have a y value of 2. When x equals 270, we have a y value of 5. So that's how you would sketch, that's how you would find the range, by sketching the simplest function and then just transforming it until you get to the function that you're looking for. So the range, we can see that the smallest y value for f of x is at 1, and the largest y value for f of x is 5. So y is an element of 1 to 5. Now if you just look at the range for y equals minus 2 sine x, because f of x is the function minus 2 sine x shifted 3 units up, if we just look at the range, which is y is an element of minus 2 to 2, and you just add 3 units to each of those minimum and maximum y values, then minus 2 plus 3 is 1, and 2 plus 3 is 5. So that's one way of going about determining the range of f. If you don't want to draw sketch graphs to determine the range, then again we're going to start with the most basic function, which is y equals sine x. Now by definition, sine x has got a maximum value of 1 and a minimum value of negative 1. Sine x can never be greater than 1, it can never be less than negative 1. So by definition, sine x is less than or equal to 1, greater than or equal to negative 1. Now to transform this into minus 2 sine x, if we multiplied this inequality, if we multiplied every single term by minus 2, we need to reverse each inequality sign. So less than or equal to will reverse, and greater than or equal to will also reverse. 1 times minus 2 is minus 2, and minus 1 times minus 2 is 2. This is not how you write inequalities. What we are looking for is 3 minus 2 sine x. So now we're going to add 3 to each of these quantities. So 3 minus 2 sine x is greater than or equal to, now because we're adding 3 to this quantity, we have to add 3 to 2 and add 3 to negative 2. So negative 2 plus 3 will be 1, and 2 plus 3 will be 5. Now this is generally not how you write inequalities. You always write sandwich or compound inequalities as such. So we are going to just rearrange this. 3 minus 2 sine x is greater than or equal to 1, so we're just going to write it like that, and 3 minus 2 sine x is less than or equal to 5, so we're just going to write it like that. And this is this is what we've been looking for, right? This 3 minus 2 sine x is f of x is less than or equal to 5 and greater than or equal to 1. This is the range written as an inequality. So y is an element of 1, 2, 5. So you get the same answer whether you draw the sketch graph or you do it algebraically. Now, incidentally, the next part of the question is to sketch the function y equals f of x. Recall that f of x equals 3 minus 2 sine x. So we already sketched that function, so this would be the green function over here. But had you not answered the question graphically, then you would still need to sketch the function. Now, because we're dealing with the trigonometric function sine, well, whenever you sketch trigonometric functions, choose values of x or theta or whatever angle you're working with that give you nice, neat integer or fractional values for y. So the values of x, or the angle that work for sine x, or the function sine, will be 30 degrees, 90 degrees, 150, 180, 210, 270, 330, and 360. So starting when x equals 0, sine 0 is 0 times minus 2 is 0, 3 minus 0 is 3. So the first point will be 0, 3. The next value of x we're going to use is 30 degrees. Sine 30 is a half. A half times minus 2 is minus 1. 3 minus 1 equals 2. So at 30 we have a y value of 2. Sine 60 will not work. Sine 60 is root 3 over 2. That's an irrational number. And you want to avoid irrational numbers because we're plotting neat values for y. Sine 90 is 1. 1 times minus 2 is minus 2. 3 minus 2 is 1. So the next value for y will be 1. 120, sine 120 is the same as sine 60. It also won't work because sine 60 is root 3 over 2, an irrational number. Sine 150 is the same as sine 30, which is a half times. Minus 2 is minus 1, 3 minus 1 equals 2. And you can see that we are now starting to repeat values. Sine 180 is 0. 0 times minus 2 is 0. 3 minus 0 is 3. So the next value at 180, we have a y value of 3. 210, sine 210 is minus sine 30, which is minus a half. Minus a half times minus 2 is plus 1. 3 plus 1 is 4. So the next y value at when x equals 210, y will be 4. Sine 240 won't work. That's minus sine 60, which is an irrational number. Sine 270 is minus 1. Minus 1 times minus 2 is 2 plus 3 is 5. So at 270, we have a y value of 5. And you can see what the next value is going to be. At 330, we're going to come down to 4. And then at 360, we will have 3. And you can do that by symmetry. And then just draw a nice, smooth curve through the points. Function g is defined by g of x equals 3 minus 2 sine x for x is between 0 degrees and a degrees, where a is a constant. State the largest value of a for which g has an inverse. Now this is essentially the same as f of x from the previous question. All they've done is change the interval and just call the function g of x. So we've already got the sketch graph for g of x, 3 minus 2 sine x. Okay, which is the top graph, the green graph. Now, this function is not a one-to-one function. It's not a one-to-one function because we have one output value for several input values. So if we just take y equals 3 and we just mark on the function every point where y equals 3, we have another point here at x equals 180. So the first one was x equals 0. x equals 180, and then y equals 3 again at x equals 360. This is a many-to-one function. Now, to restrict this many-to-one function such that it's a one-to-one function, we want to restrict it to a one-to-one function, because the only way we can find an inverse of a function is if the function is one-to-one, right? As it is right now, 3 minus 2 sine x does not have an inverse because it's not a one-to-one function. So we're going to restrict g of x such that it is a one-to-one function. If we look at the turning point of the function, right, the function becomes many-to-one beyond the turning point. So the function will start at 0, 3 and move through 360 degrees, and as it does at 90 it turns, and it turns again at 270. Now, a one-to-one function means that for every one input value, we can only have one distinct output value. So in other words, for every distinct x value, there's only one y value. So we need to restrict this function in the interval where between 0 and a degrees, such that g of x has an inverse. So in the interval where x is greater than 0 but less than a, we need to restrict g of x in such a way that we have one y value for every x value. That means we cannot go beyond this turning point. We cannot move beyond 90 degrees, because once we move beyond 90 degrees, the function starts moving up again. And you can clearly see that if we just take a y value of 2, we have a y value of 2 at 30 degrees and 150 degrees. We cannot have more than one input value for one output value. So we cannot move this function beyond 90 degrees. So in other words, we are restricting the domain between 0 and 90 degrees. So the largest possible value for a will be 90 degrees. Part 4, when a has this value, obtain an expression in terms of x for g to the minus 1x. So g to the minus 1x, which is the inverse of g of x, exists when g of x is a one-to-one function. So the value of a we established was 90 degrees. So when a is this value, find an expression for the inverse function. So to find the inverse function, g to the minus 1x, we switch the x and y values around. So x equals 3 minus 2 sine y, and now we need to find an expression for y. So we're just going to perform reverse BODMAS such that we have the y term on its own. So 2 sine y equals 3 minus x, sine y equals 3 minus x over 2, and then to get y on its own, we're basically performing the inverse sine function. So y equals sine to the minus 1, 3 minus x over 2. And you write the function in this form, g to the minus 1x equals sine to the minus 1, 3 minus x over 2. This is also sometimes written as arc sine 3 minus x over 2. Question 8. In the diagram, ABC is a semicircle with center O and radius 9 centimeters. The line BD is perpendicular to the diameter AC, and angle AOB is 2.4 radians. Show that BD equals 6.08 centimeters, correct to 3 significant figures. Okay, well, let's start with labeling what we can on the diagram. O is the center of the semicircle. AO is a radius of 9 centimeters. OB is also a radius, so we'll just mark that, 9 centimeters. OC is also a radius, so OC is also 9 centimeters. We have an angle of 2.4 radians inside sector AOB, and we need to determine the length of BD. Now, BD is a right angle triangle, so immediately you should be thinking about trigonometry, because we have an angle here of 2.4 radians. The adjacent angle, we'll call that angle O1, we can determine, which is just going to be pi minus 2.4 radians. So we know the angle O1. We have a side OB of that right angle triangle. If we want to find out the length of BD, we just have to use a trigonometric ratio. So BD over OB equals, relative to angle O1, BD is the opposite side, OB is the hypotenuse, so the ratio will be sine, and the angle is O1. So we'll just call it angle sine O1 for now. Now we need to find out what this angle O1 is. Now O1 is going to be pi radians minus 2.4. If you work in degrees, O1 plus the angle, okay, just call that O2 now. O1 plus O2 is 180 degrees. So O1 is 180 degrees minus O2. We're working in radians though. We're not working in degrees. So we have to use pi, not 180 degrees. So O1 is pi minus 2.4. So BD over OB, which is 9, equals sine pi minus 2.4. BD therefore equals 9 sine pi minus 2.4. Make sure that you're working in radians on your calculator. BD equals 6.079, but correct to three significant figures at 6.08 centimeters. The second part of the question requires us to find the perimeter of the shaded region. So the perimeter of the shaded region will be AO plus OD plus BD plus arc length AB. Right, that's the perimeter of the shaded region. We know that AO equals 9, so the perimeter of the shaded region will be AO plus OD plus BD plus the arc length of AB, of the sector AOB rather. AO we know is 9. OD, we can determine OD because we know that this angle O1, is pi minus 2.4 radians. We can again use a trigonometric ratio to determine OD. So OD over OB equals, OD is the adjacent side in triangle OBD relative to angle O1. So it's cos pi minus 2.4. OD equals OB, which is 9, cos pi minus 2.4. OD is therefore approximately 6.64 centimeters, correct to three significant figures. So OD is 6.64. BD we calculated previously as 6.08, and arc length AB is given by r times theta. AB equals the radius 9 times. Now theta is this angle here, which is 2.4 radians. 9 times 2.4 is 21.6. So arc length AB is 21.6, and then the sum of all of those will give us the perimeter of the shaded region, which is 43.32 centimeters. The last part of the question requires us to find the area of the shaded region. So the area of the shaded region will be the area of the sector AOB plus the area of the right angle triangle BOD. The area of a sector is given by a half r squared theta, and the area of a right angle triangle is given by a half base times height. So the area of the sector, the radius is 9, so it's going to be a half times 9 squared times theta, which is 2.4 radians, plus a half times the base of the right angle triangle BOD is OD, and the height is BD. It doesn't matter which one is base, which one is height. The two are perpendicular to each other, so one is the base and one is the height. So it'll be a half OD. OD is 6.64 and BD was 6.08. And that all equals 117.3856, so 117.39 centimeters squared. The curve has equation y equals 4 over root x. The normal to the curve at the point 42 meets the x-axis at P and the y-axis at Q. Find the length of PQ correct to 3 significant figures. Okay, first things first, we have a curve y equals 4 over root x. The normal to the curve. Now, the definition of a normal. The normal is a straight line perpendicular to a tangent, right? So we've dealt with curves and tangents to curves and the gradient and equation of those tangents to curves, right? When it comes to normals, a normal is just perpendicular to a tangent, so at the point of contact to the curve, right? So because we're required to find, we're given that the normal to the curve is at the point 42, so that's the point of contact. The normal to the curve meets the x-axis at P and the y-axis at Q, and then we're required to determine the length of PQ. So to find the length of a line segment, you're going to need to know what the coordinates are of the endpoints that make up that line segment. In other words, we need to determine the coordinates of P and of Q. Now, to do that, P lies on the x-axis, right? So it's an x-intercept of that line segment, and Q lies on the y-axis, so it's the y-intercept of that line segment. So we're going to need to determine the equation of PQ. That's essentially where we're going with this. So let's just start with the fact that we are given a normal to a curve, and from there we are going to first determine the gradient of the tangent to the curve at that particular point of contact, so at the point 42. So the first thing we need to do is find the gradient of the tangent, which we do by finding dy dx. So we need to get an expression for dy dx from the given curve. Y equals 4 over root x. In order to find an expression for dy dx, we need to get the curve into differentiable ready form, right? So the first thing we are going to do is just write this as a power, so it's 4 over x to the half, which is written as 4x to the minus a half. This is now in differentiable ready form. We're now going to find an expression for dy dx, right? So dy dx equals minus a half times 4 is minus 2x to the minus a half minus 1 will be minus 3 over 2. This expression represents the gradient of a tangent to the curve. Now the value of the gradient of a particular tangent we will determine and we get from the point of contact, right? So dy dx at the point where x equals 4 will equal minus 2 times 4 to the minus 3 over 2. So it's minus 2 times 2 squared to the minus 3 over 2. That's minus 2 times 2 to the minus 3, which is an eighth. And minus 2 times an eighth is minus a quarter. So this now represents the gradient of the tangent to the curve y equals 4 over root x at the point of contact 4, 2. Now the gradient of the normal to the curve at this point of contact will therefore be 4. Because the tangent and a normal are perpendicular to each other, the gradient of the tangent times the gradient of the normal has to equal -1. This is the rule for perpendicular lines. The product of the two gradients of perpendicular lines will always be -1. So if the gradient of the tangent is -1/4, then the gradient of the normal is going to be 4. Now, we have the gradient of the normal, which is 4. We have the point of contact for 2, so we can determine the equation of the normal. So we'll use y minus y1 equals m times x minus x1. You can also use y equals mx plus c. It doesn't make a difference. x1, y1 is this point of contact. So x1 is 4 and y1 is 2. So y minus 2 equals 4 times x minus 4. Y equals 4x minus 16 plus 2 is minus 14. So this represents the equation of the normal to the curve at the point 4, 2. Now to find the coordinates of P and Q, P lies on the x-axis. So where this line, this normal, cuts the x-axis will give us the coordinates of P. So the x-intercept happens when y equals 0. So 0 equals 4x minus 14. 4x equals 14. X equals 7/2. So P is the point 7/2, 0. And then likewise, the y-intercept is where x equals 0. So y equals 4 times 0 minus 14. Y equals minus 14. So Q is the point 0 minus 14. Now if we just draw a rough sketch, and the reason we're going to draw a rough sketch is because we don't need to use the distance formula. You can, obviously that works for any line segment. But if we just draw a rough sketch, and it doesn't have to be accurate. Okay, so this will be our straight line. This is P, and that is Q. We've clearly got a right angle triangle here. OP is 7/2 units, and OQ is 14 units. So we can just use Pythagoras' theorem to determine the length of PQ. So PQ squared equals OP squared plus OQ squared. So that's going to be 7/2 squared plus 14 squared equals 208.25. So therefore PQ equals the square root of that, which is 14.43. To three significant figures, it is going to be 14.4 units. The second part of the question is to find the area of the region enclosed by the curve, the x-axis, and the lines x equals 1 and x equals 4. Now, it is a very good idea. In fact, it's imperative that you draw a sketch graph before you even attempt a question like this. So here's the sketch graph. The red curve is y equals 4/√x. We then have the lines x equals 4, x equals 1, and the x-axis, which is y equals 0. Right, so we're looking for the area of the region enclosed by the curve, the x-axis, the lines x equals 1, x equals 4. Now to sketch the function y equals 4/√x, it's not a typical function that you're accustomed to. So because we've got a surd, we're dealing with a surd. Just choose values of x that will give you a nice neat value. So start with, you obviously cannot choose x equals 0 because you're going to have an asymptote, okay, on the y-axis. So choose x equals 1, and all you want is just a couple of points just to get a rough idea what the curve is going to look like. Again, you don't have to draw this accurately. We're only looking for the area of the region enclosed by these curves. So we are just looking for this shaded region over here. That's all we're looking. We're looking for the area of that shaded region. We don't need an accurate graph by any means. But just to get an idea what it looks like, pick a couple of points. So choose values of x. They'll give you a nice neat value of y. Plot those points and get an idea what the curve looks like. Draw the curves x equals 1, x equals 4, and y equals 0. So you can see what you're dealing with. So if x equals 1, we'll have y equals 4 over 1. So y equals 4. If x equals 4, then we're going to have 4 over root 4, 4 over 2. So y equals 2. And just for the purposes of this video, we're only going to put these two values in. So when x equals 1, we have y equals 4. So there's that first point there. And when x equals 4, we have y equal to 2. Now, if you just plot 2 points, you're going to get a straight line essentially. You're not going to think to draw a curve, but it is a curve, so you would have to just draw a smooth curve through those points. If you wanted to find another point, but you don't get nice values, you'd have to just approximate a point. That's fine. Whatever it may be, get 3 points, draw a smooth curve through that, draw the other curves in, and establish what the region is and the area that we're looking for. So to find the area enclosed by these curves, we are going to be integrating between x equals 1 and x equals 4. Those are your two boundary lines. And the curves are y equals 4 over x and y equals 0. Straight lines, you can't really call them, it doesn't make sense to call them curves, but you can refer to them as curves because that's what we deal with when we are integrating. So we are going to be integrating the area enclosed by these curves equals the integral. The boundary lines are x equals 1 and x equals 4. So we're integrating between x equals 1 and x equals 4 of the curve. So the top curve, which is 4 over root x, minus the bottom curve, which is y equals 0. So essentially we just have the expression 4 over root x, and we're integrating with respect to x. Here we're not quite ready to integrate this expression because we have a surd in the denominator. So we're first going to put that into integrable ready form. So that's going to be 4x to the minus a half, and we're integrating with respect to x. So we can take out this constant, 4. We're integrating x to the minus a half, so we're going to add 1 to minus a half, which gives us a half. And then we divide by a half, and we are integrating between x equals 1 and x equals 4. Okay. We're dividing by half, so it's essentially the same as multiplying by 2. 4 times 2 is 8. So we have 8 times, when x equals 4, we have 4 to the half minus 1 to the half. That equals 8 times 2 squared to the half. 1 to the half is just 1. That's 8 times 2 squared to the half. So it's the square root of 4, which is just going to be 2. 2 minus 1 equals 1. 1 times 8 equals 8. So the area will be 8 units squared. The equation of a curve is given by y equals x squared minus 3x plus 4. Show that the whole of the curve lies above the x-axis. Okay, so what information can we actually gather from this question? First of all, this is a quadratic function, right? The quadratic function either shapes like that or it shapes like that. Now, just before we draw a rough sketch of this, just note that the coefficient of the x squared term is 1, right? And 1 is clearly greater than 0. So if the coefficient of the x squared term is greater than 0, then the function is going to shape up. So we know that the quadratic is going to shape with the arms pointing up. Now for the function to lie above the x-axis, if we just draw, and we don't really care too much about the axis of symmetry at this point, okay? So this is your vertical axis, the y-axis, and your horizontal axis, the x-axis. For the function to lie above the x-axis, it clearly cannot A, cut the x-axis at all, right? So it has to shape up. So if we are looking at the topic nature of roots, right, we are basically talking about delta being less than 0 because there are no x-intercepts here, which means that there's no solution. The roots are not real. In other words, the discriminant delta is less than 0. So to show that the curve lies above the x-axis, in other words, show that there are no real roots to this quadratic, we simply determine the value of delta. So delta, this is one way to do it. There is another way to do it, and I'll do it with you shortly. Delta equals b squared minus 4ac. So that's minus 3 squared minus 4 times 1 times 4. That's 9 minus 16, and that equals negative 7. Lo and behold, delta is less than 0. So therefore, we have non-real roots, and therefore the function lies above the x-axis. That's one way to answer the question. Okay? And another way to answer this question is to write this quadratic, which is in standard form, ax squared plus bx plus c form, and we're going to write it in turning point form, which is a times x minus p all squared plus q. So we're going to complete the square, right? The coefficient, to complete the square, ensure that the coefficient of the x squared term is 1, which it is, so we don't have to do anything here. We are simply going to now add a bracket squared and subtract that same bracket squared. What we put in place into that bracket is half the coefficient of x, so we put minus 3 over 2 into those brackets. The first three terms forms a perfect square trinomial, x minus 3 over 2 all squared, and we can evaluate the last two terms. That's 4 minus 9 over 4, so that's x minus 3 over 2 all squared plus, that's going to be 7 over 4. So the turning point is the point 3 over 2, 7 over 4. Now 3 over 2, 7 over 4, let's just draw this again. 1, 2, 3 over 2 is going to be 1.5, and then 7 over 4 is 1 3/4. So we can say that the turning point is somewhere there. We know that the value of a is positive, so it shapes up. Again, we don't really care too much about any other information, but we know that the function is going to shape up like that. So by completing the square and writing it in turning point form, we can show that the function looks something like that, which we also knew from the value from the actual information given in the question, right? So that was another way of showing that the curve lies above the x-axis, because we've shown that the turning point lies in the first quadrant and the function we know shapes up because the value of a is positive. Okay, next we're required to find the set of values of x for which x squared minus 3x plus 4 is a decreasing function of x. So I've sketched an accurate graph of this function, y equals x squared minus 3x plus 4. So here's your turning point. That was the point 3 over 2, 7 over 4, the turning point. Now, to show that a function is a decreasing function, sorry, we're not showing that it's a decreasing function. We need to find the set of x values for which it is decreasing. Now, a function is decreasing, so if we just call this f of x, I'm just calling it f of x because it's, when working with derivatives, it's just a nicer notation to use f prime x rather than dy dx. Now, for a decreasing function, so for f of x to be decreasing, then f prime x needs to be less than 0. And for f of x to be an increasing function, f prime x must be greater than 0. Just remember that f prime x represents the gradient of a tangent to a curve, right? This is your curve y equals x squared minus 3x plus 4. You can draw a tangent at any point on that line, right? If the gradient of that tangent is positive, right, then the function f of x is an increasing function. And conversely, if the gradient of a tangent is negative, so the tangent would slope to the left, then if the gradient is negative, then you have a decreasing function for all x values for which you have a tangent sloping to the left, right? So the set of x values for which this function is a decreasing function, if we just take that turning point, any value of x less than 3 over 2, 1.5, you can draw a tangent line to that curve, and that tangent line will slope to the left. In other words, it has a negative gradient. So to answer this question, for x less than 3 over 2, f of x will be a decreasing function. The equation of a line is y plus 2x equals k, where k is a constant. In the case where k equals 6, find the coordinates of the point of intersection of the line and the curve. Okay, so our curve is y equals x squared minus 3x plus 4, and the straight line is y plus 2x equals k. I'm just going to write that as y equals k minus 2x. Now for points of intersection, we equate two functions equal to each other, right? And they are telling us that in the case where k equals 6, find the coordinates of these points of intersection. So for k equal to 6, the straight line will be y equals 6 minus 2x. Now for point of intersection, we are going to equate these two functions. So if we want to call this f of x and we want to call that g of x, then for points of intersection, f of x equals g of x. So x squared minus 3x plus 4 equals 6 minus 2x. We now just need to get this into standard quadratic form and solve for x. So x squared minus x minus 2 equals 0, which will factorize as x plus 1 times x minus 2, x equals minus 1 or x equals 2. These two x values, minus 1 and 2, represent the x coordinates of the points of intersection. So to get the y coordinates, we're just going to substitute both of these x values in to the simple equation, which is your straight line. You can substitute into the quadratic as well, just more time consuming. So for x equals negative 1, y equals 6 minus 2 times minus 1. So y equals 6 plus 2, which is 8. So your first point of intersection is minus 1, 8. You can just call that point A if you like. And then for x equal to 2, y equals 6 minus 2 times 2. 6 minus 4, y equals 2. So the other point of intersection is the point 2, 2, which we'll call point B. Finally, find the value of k for which the line is a tangent to the curve. Okay, so just recall that the curve is y equals x squared minus 3x plus 4, and the straight line is y equals k minus 2x. Now we want to find the value of k for which the line is a tangent to the curve. Now, a tangent to a curve, recall that a tangent is a straight line that cuts a curve at one distinct point. There's only one point of intersection between the tangent and the curve. So when it comes to equating two functions equal to each other, right? For points of intersection, we always equate two functions equal to each other, right? So x squared minus 3x plus 4 equals k minus 2x. Now for 2 points of intersection, this would imply two real unequal roots. In terms of your discriminant, that means that delta is greater than 0. For 1 point of intersection that's real equal roots, delta would have to equal 0. For no points of intersection, non-real roots, delta will be less than 0. So you need to just bear that in mind. So what we're going to do here is we're just going to get this into standard quadratic form, take all the terms over to the one side, equate it to 0, and then determine the discriminant from that. So x squared minus x plus 4 minus k equals 0. A equals 1, b is negative 1, c equals 4 minus k. So delta equals b squared minus 4ac. That's minus 1 all squared minus 4 times 1 times 4 minus k. That's 1 minus 16 plus 4k. So delta equals 4k minus 15. Now if delta is positive, we'll get 2 points of intersection, 2 real unequal roots. 1 point of intersection, delta must be equal to 0. So this is what we're looking at here, because we want to know the value of k for which the line is a tangent to the curve. In other words, there's only 1 point of intersection. So we equate 4k minus 15 equal to 0 and solve for k. So k equals 15 over 4. If k is 15 over 4, then this line will be a tangent to that curve. And we can verify the solution by drawing an accurate graph of both functions, y equals x squared minus 3x plus 4 and y equals 15 over 4 minus 2x. And we can clearly see that there's 1 point of intersection. The straight line is a tangent to the curve.